Hi, welcome to Problem Solving Experts. In previous videos, I have talked about how to calculate our baseline performance, defining how big the problem is. But that performance that we have calculated can be using DPMO when you are having attributes, PPMs when you are having continuous variable data, or also you can use the raw throughput yield or normalized yield when you are having several metrics. In any case, that is not the real performance of your process or product, but that is what is called the apparent performance. Why is that? Well, let me explain that with this one. Usually we are having in a process inputs and we are having outputs of the process. For instance, if we want to know the performance of the product that is going out from the process, well, what we have to do is to inspect or measure the product. Then what we have to do is to take the part and use a measurement system to obtain data. With the data that we are obtaining, we are going to calculate a mean and a standard deviation of the data. And using those values, we will be calculating our baseline performance, sigma value, PPMs, etc. But, well, in reality, the mean of the data is not exactly the same than the actual mean of the process or product. But the mean of the data is the mean of the product plus the error of the measurement system. So we are having a bias created by the measurement system, and that will be the mean of the data. That happens also, for instance, for variability. The standard deviation or the variability of the data is not exactly the same than the variability of the product or the process. But the variance of the product or process plus the variance of the measurement system is equal to the variance of the data. Then we have calculated our performance using the mean of the data and the standard deviation of the data, but again, those values are not the actual values of the product or process that we want to evaluate. So what do we have to do before doing a cause and effect analysis? We have to make sure that the measurement system is not introducing too much noise to our data. So we have to validate the measurement system, how accurate and how precise is our measurement system. So we have to do some studies to validate our measurement systems. Sometimes the error of the measurement system or the variability of the measurement system is huge. And then the variability that we are observing in data is not at all related to the variability that we are actually having in our process or product. But we are measuring noise because of the measurement system, and therefore any analysis that we will be doing, cause and effect analysis, is useless because, again, the conclusions won't be right, and then the actions won't be effective, and all of that is because we have analyzed noise and not the real signal of the product or real signal of the process. So, unfortunately, it is very frequent that people ignores the effect of the measurement system. And when we are taking a look to the data, we assume that those values are corresponding to the actual values of the process or product. Just to give an example of what I am saying, let me share this story about how a measurement system problem can introduce or can lead to a big problem. Let's take a look to this story.
October 1707. Fact: Great Britain lost 4 warships and 2,000 human lives, more deaths than the Titanics. There was no battle. Problem: It was nighttime and there was fog. Admiral Claude Beasley Shovel made a miscalculation regarding their position in the Atlantic Ocean, and his insignia ship crashed against the rocks of Scilly Island. The rest of the ships blindly followed the insignia ship. Cause. Latitude and longitude already existed since the 1st century before Christ, but in the 18th century, a way to accurately measure longitude was not known. Distance traveled and speed were approximations, and a wrong measurement led to miscalculations resulting in a catastrophe. Measurement system used. A wooden log was dropped to the ocean at the front part of the ship. The time that it was taking to the log on water to get from the front part of the ship to the rear of the ship was measured. Knowing the length of the ship, the speed was calculated by dividing the length of the ship over the time it took to the log to travel that distance. Longitude traveled by the ship was calculated by multiplying the time traveled times calculated speed. Positioning at the map was estimated by the longitude calculated and the direction taken. Therefore, it is obvious that many errors and huge uncertainty of the measurement system were involved.
In this video, I will talk about studies to evaluate the variability of the measurement system. In reality, there are many studies that can be used to evaluate the measurement system, to evaluate how big is the variability or how much is the error of the measurement system. For instance, if we want to evaluate the error created by the measurement system, which is introducing a bias to the mean of the actual mean of the process or product to get the mean of the data, we can do some calibration studies. And those calibration studies, for instance, can be accuracy study, linearity study, and stability study. But well, again, I will be talking about those later. In this video, I will be talking about how to calculate the standard deviation of the measurement system. To calculate the measurement system of the standard deviation, we can do some studies, for instance, precision studies. And these precision studies can be uncertainty studies, a GR&R type 1 method, GR&Rs, which can be short method, long method, and for the destructive test. For long method, we can have the mean and ranges X-bar-R method or ANOVA cross method. In this video, this time, I will be talking just about uncertainty studies. The intent, of course, is to have videos for all these methods. When we are having attributes, we are having expert reevaluation method, we can have round robins method, and also we can report the performance in terms of percentage of right decisions and kappa index. For ordinal evaluations, which is very good, bad, very bad, for instance, instead of good or bad, pass or fail, then we can use the round robins method again, but reporting the Kendall index. And of course, for calibration studies, as I have said, I can do accuracy, linearity, stability method. And also there are some other methods. For instance, for the long method, we can have the mean and ranges method or ANOVA cross method. And for destructive test, we can have ANOVA nested. So as I have just said, I want to cover all these methods in different videos, but in today's videos I will introduce the basics of the precision studies through the uncertainty study. Let's start with the uncertainty study. We are calculating now the variability of the measurement system. It's very important to highlight the term measurement system because we want to evaluate the variation introduced by the whole system, by all the elements of the measurement system, which can be including the variability due to human factors, but also variability because of the measurement equipment, the equipment that you are using to measure, also variability because changing the environmental conditions, etc. The method, the procedure that is being used also can be introducing a variation to the measurement system. So everything related, or the whole system, or all the components, all the elements in the system that are creating variability while we are doing a measurement will be part of the variability of the measurement system. It's important to highlight that because now I will be talking about uncertainty, but this uncertainty won't be the typical uncertainty that is reported in a calibration certificate of the uncertainty of an equipment. I'm not talking about that specific uncertainty of that specific equipment, measurement equipment, but the uncertainty because the whole measurement system. Then, when should we use an uncertainty study if we are doing, for instance, a project to improve something in the process? Well, when usually the measurement is done only by one person, the same equipment, under the same environmental conditions, or the same part of the plant or any place or location where the measurement is done. If all is done the same way, with the same people, with the same equipment, then we can use an uncertainty study. The intent is to calculate the standard deviation of the measurement system. In this case, we are having the variance of the measurement system. Of course, the bigger the variation of the measurement system, the bigger will be the variability of the data, because as I have said, the variability of the data is the variability of the process plus the variability of the measurement system. So now we want to calculate how big is the variability of the measurement system. And then that's what we have to do. We have to uncertainty study. We are going to use the same part, one part, the same equipment, the same appraiser, the same inspector, at the same place, measuring that part several times. So we are taking the part, doing the entire measurement process, and getting the result. Same part, same person, same equipment, same place, measure again. Same part, same equipment, same place, measure again. And so on. By the way, that also is known as a repeatability study, because again, we are repeating the same measurement several times. And the variability resulting of repeating the same measurement, same person, same equipment, same everything, will be, well, the variability of the measurement system. The variability created by the method and the person and the equipment and everything. Let me take this example. Let me say that I want to evaluate viscosity and of one specific solution. And the viscosity to measure the viscosity of that specific solution, I will be using a viscosimeter. And basically that is, let me say, let me say it's a tube, a hose made of glass. I fill it with that solution, and all what I have to do is to, well, release, and then the liquid will be going down, going down, going down, going down. The higher the viscosity, it will be slow. It will be more slowly the pace than the liquid is going down. So basically, all what I have to do is to use a stopwatch and measure how much it takes to the solution, to the liquid, to get from this mark to this second mark. So actually I am measuring time, and later, well, I can have a table that this time corresponds to this viscosity, this other time corresponds to this other viscosity. So I have an equivalent to convert the time into viscosity. But in reality I'm measuring time, and I want to, of course, evaluate how big is the variability because of the measurement system. So all what I have to do is to use the same viscosity, the same solution, the same person, measuring time several times. And with that, we can calculate the standard deviation of time. By the way, in previous videos, I have talked about how to calculate the mean, the standard deviation, or the mode, the median, the variance, all of that. So take a look to descriptive statistics. That's a video. There's a video about descriptive statistics, and I'm not going into those details right now. So let's say that the standard deviation of time is 0.135 seconds. Usually, the standard deviation of the measurement system is expressed as small u, and that is known as standard uncertainty. And well, let me just make it simple. The standard uncertainty is nothing else but the standard deviation of the measurement system. Well, that's the first term, which is the standard uncertainty. The next step usually is to report the extended or expanded uncertainty. And that uncertainty is capital U equal to a factor, that factor is known as coverage factor, times the standard deviation of the measurement system or the standard uncertainty. The most typical value that is used as a coverage factor is K equal to 2, which will be the total variability of the measurement system. And basically, a K equal to 2, that means 2 standard deviations, which is the mean plus minus 1 standard deviation. As I have said in previous videos when I was talking about normal distribution, then the mean plus minus 1 standard deviation is equivalent to 68% of the area. Well, usually, what I recommend is not to use plus minus 1 standard deviation, but the total variability of the measurement system can be what I will be calling repeatability. And the repeatability is equal to 5.15 standard deviations of the measurement system. 5.15 standard deviations of the measurement system, that is plus minus 2.575 standard deviations, leading to 5.15 standard deviations. The area for the normal distribution is 99%. So that's my recommendation. Of course, some people they prefer to use plus minus 3 standard deviations, some other they prefer to use plus minus 2 standard deviations, which is 95%. I prefer to use 99%. And that 99% will be the total variability because of the measurement system. So for this example, for this specific example, then I would say that the repeatability, let me call it gauge repeatability, is equal to 5.15
times
0.135 standard deviations, in this case seconds. Then the total variability, gauge repeatability, is equal to, let me do the calculation. Okay, then the repeatability, the total repeatability is 0.695 seconds. If we divide that by 2, we can get plus minus 0.348 seconds. So, well, that is the total variability of the measurement system. Now, the question is that a lot or is that small? Is that acceptable or is that not acceptable? Well, the answer is it depends. It depends what you are measuring. For instance, let's say that I want to cook a soup. I'm cooking a soup. And of course, I'm measuring how much time it takes to cook a soup. And let me say that this is an instant soup, and all what I have to do is to, to put the soup during 3 minutes in a oven, and that's it. And I want to measure time of the 3 minutes. If I'm having an error of plus minus 0.34 seconds while I'm measuring 3 minutes to cook the soup, the error is very small. Is really not a problem. But for instance, if we are at the Olympic Games and we are having a competition of 100 meters race, and the error of the measurement system is 0.348 seconds, that is huge. That's really big error if we are measuring time in a race of 100 meters run. So it depends. Is this good or is bad? It depends. So now it depends on the tolerance. It depends of what you are using this for. So let me talk about that. Let me talk about the acceptance criteria. Let's do that. Acceptance criteria. We have to compare the variability of the measurement system against, we have two options. The tolerance, and with that one we are going to get the percentage of repeatability or percentage of variability of the measurement system against tolerance, or or can be both, or any of both, the variability of the measurement system against the process, against the total variation observed. And we are going to call to that one percentage of repeatability or percentage of variability of the measurement system against process. And of course we can have those two criteria to decide if it's if it's an acceptable measurement system or not. Usually, if we are talking about the criteria from the customer point of view, we are using the percentage of variability of the measurement system against tolerance. But if we want to know if the measurement system is good, is acceptable, is not introducing too much noise while we are controlling a process or a product, then I would recommend to use the percentage of variability of the measurement system against process. One is not excluding the other one, but usually is to focus more on one or the other one, depending if your focus is the customer or if your focus is internal process control. Well, let me talk first about percentage of repeatability against tolerance. So the percentage of repeatability or percentage of gauge R, it will be the repeatability divided by the tolerance times 100. And that's it. That will be the percentage of repeatability against the tolerance. Now the big question is, what is the tolerance? How can I calculate the tolerance? Well, the tolerance, we are having several possibilities. One option is the tolerance is equal to upper specification limit minus lower specification limit. And that's it. That will be the way to calculate the tolerance. Now, that is applicable when you are having two-sided specification limits. But what about if you are having one-sided specification limit? You have a lower specification limit and greater is better. Or you are having an upper specification limit and smaller is better. If that is the case, then we are having two options. For those two options, it will be the tolerance. Well, the option is basically, the first option is 2 times the absolute value of the specification limit minus the target. If you are having a target for the mean, that will be this one. If you don't have a target for the mean, then the tolerance is equal to 2 times the specification limit minus the historical mean of the process. Let me call it apparent. Remember that apparent is the mean that we have calculated from the data that we have collected from the process, not the measurement system, but the total process, the historical performance that we have had. If that is the case, then using that mean and the specification limit. The specification limit can be an upper specification limit or a lower specification limit, depending on the type of specification limit that we are having. Now, for this specific example that we had before, for the viscosity that we actually were measuring time, I said that the repeatability was 0.695 seconds. But also I'm having here the specification limits. 6.5 seconds is the upper specification limit, and the lower specification limit is 4.5 seconds. For that case, then the tolerance will be equal to upper specification limit, which is 6.5 seconds, minus lower specification limit, 4.5 seconds. Then the tolerance is 2 seconds. With that one, we can calculate the percentage of repeatability. The percentage of gauge repeatability is the total repeatability that we are having here, 0.695 seconds, divided by the tolerance which is 2 seconds, times 100. Then the percentage of GR&R, of repeatability is 34.75%. And well, that is the total variability of the measurement system. What is the acceptance criteria? By the way, keep in mind that this is against tolerance, percentage of repeatability against tolerance. The acceptance criteria is, if the total variability of the measurement system is smaller than 10%, we are having a good measurement system. It is acceptable. If the total variability of the measurement system against tolerance is greater than 30%, then is not acceptable. For this example that I'm having, because the variability of the measurement system is greater than 30%, then this measurement system is not acceptable. And well, what do we have to do if we want to improve the measurement system? Well, let me talk about that next. What to do to improve the measurement system. If the measurement system against tolerance is not acceptable because the total variability is greater than 30%, well, one recommendation can be to standardize the measurement procedure. So although we are using the same person, the same part, the same equipment, the same place, several measurements, by the way, a typical question is how many measurements should we do? Usually, it is recommended to do at least 10 to 15 measurements. I prefer, honestly, if not very expensive, not very time consuming, to do 25 to 30 measurements. 25 to 30 will be much better, but of course usually it is said that 10 to 15 is good enough. Well, let me go back. Although we are doing the same measurement several times, very likely the person is not standardized by himself, herself. And then we have we have to make sure that the person will be standardized with themselves. They are standardized with themselves. That will be the first thing to do. Second one, make sure that the equipment is very well maintained. Make sure that it is clean, it is adjusted, it is well, if necessary, to be aligned, to put oil on it, etc. So maintain the equipment. Of course, you have to control the environmental conditions. For instance, if you are measuring length or thickness or something, but the environmental conditions are changing a lot of high temperature, low temperature, well, there will be contractions, expansions of materials, and you're having variability on the measurements, but because the environmental conditions are changing. If there is a lot of vibration and you have a scale, and because of that vibration, the scale can be also changing the values, make sure to do something to eliminate that vibration, etc. So control the environmental conditions. If that is not enough, very likely is with what you have is not possible to get the variability that you need. Then we are having two options if that is the case. Option number one, change the method and or change the technology that we are using to do the measurement. Maybe the technology that that equipment is being used is not sensitive enough, is not good enough to have the variability that we need. And and then we have to get a more advanced, from a technological point of view, equipment in order to get smaller variability on the measurement or change the method that we are using. Or option number two, no, that's very expensive, or it's not possible to get that one for any reason, or it doesn't exist something better than what we have, but still the variability is very high. If that is the case, then we have to rely on a more time-consuming and expensive measurement, which is using the same equipment, using the same method, using the same environmental conditions, everything, but before doing a measurement and reporting immediately the result of the measurement, instead of doing that, recommendation is to measure several times that measurement. And the average of those M measurements will be the value that you will be reporting as a result of the measurement. With that one, you are going to reduce the variability because of the measurement. And that is because there is a principle, and that principle is that the standard deviation of the means is equal to the standard deviation of the individual values divided by the square root of m, the square root of m. For instance, I know that for viscosity, the example that I have talked before, my total repeatability, percentage of repeatability against tolerance is 34.75%. And let's say that I cannot get any better measurement system than the one that I am using. Everything is calibrated, the environmental conditions are under control, so nothing else can be done. Then instead of taking one sample of the solution, doing the measurement and reporting immediately the time or the equivalent viscosity, instead of doing that, I will take the sample, I will measure, let's say 4 times, I will measure 4 times that solution, and with those 4 times that I am measuring, then I will be getting the average of those 4 measurements will be the ones that I will be reporting. If that is the case, then the standard deviation of the mean is equal to the standard deviation of the individual values. I have said before that the standard deviation of the measurement system is 0.135 divided by the square root of 4, because as I have said, m is equal to 4. And we are going to do 4 measurements, and we are going to report the mean of those 4 measurements. Then that is equal to a standard deviation of 0.0675 seconds. With that one, we can calculate the percentage of repeatability. The percentage of repeatability, gauge repeatability against tolerance, is equal to 5.15 standard deviations of the measurement system divided by the tolerance times 100. In this case, 5.15 standard deviation of the measurement, which is 0.0675, divided by a tolerance, which is the difference between the upper and the lower specification limit, 2 times 100. And well, the expected value is actually half of this, which is 37.5% of repeatability or total variability because of the measurement system. As you can see now, the variability of the measurement system can be reduced, and that is because you are doing m measurements and you are reporting the average of the m measurements, because the standard deviation of the means will be smaller than the standard deviation of the individual values. Now, question, is this acceptable or not acceptable? I have said that if the percentage of variability against tolerance is smaller than 10%, that is acceptable. If it is greater than 30%, is not acceptable. But what about if between 10 and 30%, which this is the case, 17.37%. Is that acceptable or not acceptable? Is good or not good? Well, the answer will be, it depends. It depends on what? It depends on the variability of the process. So now I would like to talk about how the variability of the process impacts to the acceptance criteria. If the variability of my process is very small, I will need a smaller GR&R against tolerance. If the variability of the process is very big, well, maybe it's okay to have 17%, and I can accept a greater percentage of GR&R against tolerance. I will explain that, doing the next exercise. Let me do that. As I have said, the variability of the measurement system can be acceptable or not, depending on how big is the variability of the process. In order to explain that, I will be presenting 3 scenarios. The first, in all 3 scenarios, we are having the same variability of the measurement system, which is a standard deviation of the measurement system equal to 1 for all 3 cases. But in first scenario, the variability of the process, the actual variability of the process is 1. For the second scenario, the actual variability of the process is 10, and for the third one will be 100. Keep in mind that I have said that the actual variability, the real variability or variance of the process or product plus the variability of the measurement system is equal to the total variance observed, the total variability or the total variance of the data. Having that in mind, then I will be doing the calculations here to see the effect of the measurement system on the total variability because of the due to the measurement, the total variability on the data because of the error introduced by the measurement measurement system, the error introduced to the data because of the measurement system. So basically I will write here, just to keep in mind, that the variance, real variance of the process or product plus the variance of the measurement system is equal to the total variance observed. Okay, let's take a look to the first scenario. In the first scenario, the standard deviation real is 1. The standard deviation of the measurement system is 1. If that is the case, then I want to calculate the total variance. So for this case will be then 1 square, which is this one, plus 1 square, which is the standard deviation of the measurement system, is equal, and a square root is equal to the total standard deviation that we are observing. For that, we are having a square root of 2, and then that's 1.414. Then the total variance that we are having is 1.414. The real variability of the process is 1, and the variability of the measurement system is 1. Then the variability that we are collecting, that we are obtaining on the data, will be 1.414. What is the error? The error will be the difference between what we are observing from the data and the real value. And that difference will be the error. If the real value is 1, but we are observing in our data a standard deviation of 1.414, this difference is the error, and the error is 0.414. Seconds, how much is that in terms of percentage of error? The error, 0.414 divided by 1 times 100. So 0.414 divided by 1 times 100. Then the percentage of error will be equal to 41.4% of error. As you can see, the measurement system is introducing a very big error on the observed data that we are collecting. Second scenario, the real variability is 10. The variability because of the measurement system is 1. What is the standard deviation that we are expecting to have in our data? So, well, real variability is 10 squared plus variability of the measurement system, 1 square, all of that is a square root, then that's equal to 101 square root. Let's do the calculation for that. Then the square root of 101 is 10.05. So the total standard deviation that we will be observing in our data will be 10.05. How big is the error? The error is the difference between the real standard deviation and the standard deviation that we will observe in our data. Then that difference is 0.05 seconds. How much is that in terms of percentage of error? 0.05 divided by 10 times 100. That is 0.05 divided by 10 times 100. That is an error of, let me see, 0.5%. So as you can see, the same variability on the measurement system of 1 for the second scenario is introducing a small error to the data. The error introduced by the measurement system is just 0.5%. And well, let's take a look to the third scenario. For the third scenario, we are having that the total variability of the process or the product is 100, and that is a square, plus the standard deviation of the measurement system, which is 1, the square root of 1, that is 10,001 square root. Then the standard deviation observed, apparent, total is equal to, let's take a look to this calculation. then the square root of 10,001 is equal to 100.005. Then the expected standard deviation to observe in our data will be 100.005. The error is the difference between the actual standard deviation and the observed standard deviation, which is 0.005 seconds. In terms of percentage, will be 0.005 divided by 100 times 100. That's an error of 0.005%. As you can see, in all three cases, we are having the same variability on the measurement system, 1, 1, 1. But for the first case, the error introduced by the measurement system to the data is huge, is very big, 41%. But in the last case, the error introduced to the data by the measurement system is really, really small. So the same measurement system is introducing different amounts of magnitude of error to the data, depending on how much is the variability of the actual process. Then that's why it is highly recommended not to compare just the total variability of the measurement system against tolerance, but also compare the total variability of the measurement system against the total variability observed. And that total variability observed, well, can be the historical standard deviation that we have used to calculate our baseline performance, the one that we did use to calculate our PPMs and our sigma value for continuous quantitative data. Then it is said that if the percentage of total variability of the measurement system against process is smaller than 20% of the total variability of the process, we are having a good measurement system because the measurement system is not introducing a big error on the data. But if the total variability, the percentage of variability of the measurement system against process is greater than 20% of the total variability, I mean of the total variability that we observe, more than 20% is because of the measurement system, then the measurement system will be introducing a big error on the data. And then we will be having a lot of noise because of the measurement system. So we shouldn't continue until we fix the measurement system. Now I will be talking about how to calculate specifically the percentage of repeatability, the percentage of the variability of the measurement system against process. Let's do that. Well, then let me show you how to calculate the percentage of repeatability against process. In reality, it's not process, but it's against the total variability that we have observed while doing our baseline performance. Then I would say that the percentage of repeatability, gauge repeatability, is equal to the standard deviation of the measurement system square, which actually is the variance, divided by the standard deviation total square, which is actually the variance as well, and all of that times 100. What is the total standard deviation? The total standard deviation is this total standard deviation, which is the variability of the data. Keep in mind that this standard deviation of the data is the variability actual of the process, which we don't know how much is that one, plus the variability of the measurement system. So that's what we call the apparent performance of the process. And that will be the total, also is known as process standard deviation. For this specific example, I would say that the standard deviation of the measurement system, we have calculated that the standard uncertainty, which is the standard deviation, is 0.135 seconds divided by, and all of that is square, divided by the total variability observed. Let me say that while doing our baseline performance, the data that we did collect from our process and after and measuring that using our measurement system, which is the total variability that we have observed, is 3.47 seconds. So 3.47 seconds square times 100, and that will be the percentage of repeatability against process. Well, let's do the calculations. Well, this variance ratio is equal to 0.15%. If we are using the variance ratio, the acceptance criteria is if smaller than 2% is good, if greater than 7.7% is bad. Now, the automotive American industry, which is known as AIAG, they use a different way to calculate the percentage of GR&R against process. And let me do this one. Let me say that is done by the AIAG, which is for General Motors, etc. So that's the automotive industry. So the automotive industry, they actually use the standard deviation of the measurement system divided by the standard deviation total times 100. Instead of ratio of variances, is a ratio of standard deviations. In this case is 0.135 divided by 3.47 times 100. For that case, then we are having done the percentage of GR&R against process, 0.135 divided by 3.47, that is 3.89%. So basically, the criteria here is if smaller than 20%, this one, it is acceptable. If greater than 20% is not acceptable. So the percentage of GR&R against tolerance is 17.375%, and the percentage of GR&R against process, if we use the criteria of the AIAG, the automotive industry, is 3.89%. We are having a variability of the measurement system, in this case a variability because of repeatability of 0.696 seconds. So let's say that this is the variability of the measurement system. The variability of the measurement system is 0.696 seconds. And that is the repeatability, gauge repeatability. That variability of the measurement system, if we compare that variability against the tolerance that is required by the customer, which is the upper specification limit minus the lower specification limit, that variability represents 34.75% of the tolerance. 34.75% of the tolerance. Because the tolerance is actually 2 seconds. And that variability actually is representing the same variability of the measurement system, is representing only 3.89% of the total variability that we are having. And that is because the standard deviation of the process is 3.47 seconds. If we say that this variability is 5.15, 3.47, well, basically is more than 15, between 15 and 20 seconds. So of these 0.69 seconds of 15, 18 seconds, well, that's only 3.89%. That means that the total variability that we are having because of the measurement system won't be introducing big noise to the observed data that we are collecting from the process, because it's smaller than 20%. But of course, this measurement system is not acceptable to the tolerance that is requested by the customer. So recommendation is that is conditioned the measurement system. That means, what means conditioned? You can continue using this measurement system right now, because this measurement system is not introducing noise to your data. But you have to improve that measurement system, because eventually when you improve your process, eventually when you reduce the variability of the process, then that measurement system won't be acceptable. So that's why, before not becoming acceptable, try to improve it, so when you get a variability of the process is smaller than the tolerance, then the measurement system will be acceptable. Well, basically, that's what I wanted to share today. In future videos, I will be talking about GR&Rs, different type of methods that I have said that they do exist, and also for attributes, which is round robin, expert reevaluation, Kendall method, etc. Thank you very much.